Okay, for part 2 of today's online class, we're going to look at RC circuits. Here you see a circuit with a 12-volt battery, a capacitor, and a resistor all hooked up in series. And let's see what happens when we first put the battery into the circuit and start charging the battery up. So here we have a battery, a capacitor, and a resistor. Capacitor and resistor are on the right. Up above, I've got a little switch so I can start charging up the capacitor at any moment. When I close the switch, notice what happens to the current meter on the left part of the screen. As I close the switch, the electrons start moving, and when we look at the current graph, notice that the speed, the rate at which the currents are moving, started out high and it's beginning smaller and smaller and smaller as the plate charges up. Actually, let's reset that real quick and watch it again. Notice again when the system's completely discharged and we first hook it up, the electrons start moving the fastest, and then slowly as the capacitor builds up, it asymptotically approaches zero current. Notice if I reset this often, we should end up getting the curve that you wanted to see in lab this week. This is like a really slow motion oscilloscope. Okay, let's see if we can figure out the math of how this works. So here's our circuit. Let's say that we have charged it up. So that means we've built up a whole bunch of positive charges on one side of the capacitor and a whole bunch of negative charges on the other side. And let's say it's been built up for a long time so that the capacitor is as charged as we can reasonably expect it to get. Then what we're going to do is we're going to take out the battery and we're going to just connect the two ends of the circuit. So actually we didn't need to take out the battery. We could have just shorted it like we did right here. No, sorry, we need to take the battery out. Never mind. As soon as we connected the two parts of the circuit, the electrons were free to flow back to the other side of the capacitor. Let's see if we can work out the math on how this would work. So our new circuit is, we've got a closed loop. We took out the battery. We have just the capacitor and the resistor. Remember that Kirchhoff's loop law says that as we go around the circuit, that the total voltage has to be zero. So in other words, the change in the voltage as we walk around the circuit's loop has to add up to zero. Whenever we go across a resistor, remember that the change in voltage is IR. And whenever we go across a capacitor, remember that the capacitance is the charge per voltage. That means that the voltage is charge over capacitance. So that means that for this closed loop circuit as it's discharging, IR has to equal minus Q over C. Now remember that current is the charge going by per second. It's the number of coulombs per second flowing through, the number of electrons going through your circuit. So in other words, the I is the amount of charge going by per unit time, and IR equals negative QC. Now, we are calculus students, so that means we don't write delta Q, but rather we write dQ dt times R is going to equal negative Q over C. And if we wanted to find how the charge had built up over time, we want to solve this equation for Q. So let's try isolating for Q. We're going to put Q all on one side and everything else on the other side. So we've got a dq divided by a q when we move the q over to the left. And then we're going to move the dt over to the right. And the RC is going to go together on the bottom. And make sure you don't forget the minus sign. Okay, all the Q's are on the left side, all the T's are on the right side. R and C are just a constant, so they can hang out wherever you want them. To solve for this, we're going to integrate. And we're going to integrate from the initial charge to the final charge on the dq side, and we're going to integrate from 0 to t final, or just t, on the right-hand side. On the left side, dq over q, the integral of, is natural log. And don't ever forget your limits. And on the other side, the dt just goes to a t. And again, we're going from 0 to t. As we finish this up, we see that this ends up giving us that the natural log of q final subtract the natural log of q initial is going to equal minus t over rc minus a negative 0. Remember from math class that the natural log of qf minus natural log of q naught is going to equal the natural log of qf over q naught by that neat little natural log rule that you did at some point in your past, is going to equal negative t over rc. And then, if we wanted to solve for q, which is our original goal, we have to take the the exponential of both sides, and we're going to take an e of this and an e of that, and an e of a natural log. Well, they kind of go away, and you're going to get that a q final over q initial is going to equal e to the minus t over rc, or just solving for q final, we are going to end up getting that q final is going to equal q initial times e to the minus t over rc. And this should look like the form of what we found the current and the voltage to be in lab. If we were using a voltmeter across the capacitor, remember that the voltage across a capacitor is equal to Q over C. So that means the voltage across the capacitor will always be proportional to the amount of charge stored on the capacitor. And across the resistor, remember that V equals IR. If we wanted to find the current in the circuit at any point in time, we take the derivative of the charge, and remembering that dq dt is defined as the current, the amount of charge moving by per second, that means that the derivative of that right-hand side is going to look something like this. So notice that both the current and the amount of charge follow the same exponential decay curve. So it doesn't matter if you're looking at current or charge, you end up getting that exponential decay. Okay, so let's look and see what this means graphically and mathematically. In lab, we were measuring the voltage, and because voltage and charge across the capacitor are related, we get that the voltage as a function of time across the capacitor is going to equal that initial voltage we had when the capacitor was completely charged up times e to the minus t over RC. Graphically, this function is going to look something like this. If we put voltage up here and time down here, and we start at a certain voltage, it's going to exponentially decay to asymptotically approach zero discharge. Now, let's say we had a sample question of sorry. Let's see if I can get this pointer to work right. Let's say we had a sample question that asks for when does the RC circuit decay to half of its original voltage once the circuit is closed. Well, so what we do is we want the voltage across the capacitor final to equal 1/2 of the initial voltage. Plugging that into the above equation, we get 1/2 V0 is going to equal V0 times e to the minus t over RC. Notice that the voltages nicely cancel out, although I could give you a problem where there were specific numbers, which I guess half is a specific number, but hopefully you get the idea. To solve for t, the when in this problem, we need to take the natural log of both sides. So we end up getting that the natural log of 1/2 is going to equal minus t over RC. We could then solve for time. We're going to get negative RC times natural log of 1/2. In which case we now have the answer. Notice the natural log of 1/2 is a negative number, so you end up getting a positive overall time. If you know your resistor and your capacitor values, then you know how many seconds it took for the capacitor to decay. Okay, I'm going to wrap that up now. Have an excellent weekend. Try the conceptual problems that you can find on Mastering Physics. That'll be today's set of PRS questions. And drop me an email if you have any questions. Thanks a lot for tuning in. Bye-bye.